Hello, PCCL channel greets you. What is radioactive decay? I'll start with an example. I chose the 131 isotope of iodine, which is unstable. It decays to give a stable nucleus of xenon 131. We don't know when this will happen. The disintegration is random. That is to say, unpredictable. The date of the disintegration is not known in advance. On the other hand, the statistical law which governs the decrease of this population of radioactive nuclei is known. She looks that way. If the mathematical formula that describes this function is not in the program, you can be given this curve already drawn and asked to work with it. I will speak about the function in another video. Let me not forget to specify that here, either you have the number of nuclides, or you have the activity. The two are related, of course. A double number has double activity. There is a constant between the two, which is the decay constant. I choose one of the two. Since it is necessary to choose, I will choose the number n. I'm not going to spend too much time on iodine-131. I'm still giving you some keywords, for the sake of consciousness, to tell you what it is about, and you will search with these keywords if you want to know better this isotope. I wanted to talk to you about the half-life, also called half-life period. So half suggests that we are going to get half, where there are only half of the nuclides we had at the start. If the decay curve, already drawn, is given, you can be asked to graphically find the half-life, that is to say the date to which this situation corresponds. To have only half of what we had at the start. You can find it. You read it here. It's been some 8 days. We rate it D-half. 8 days for iodine-131. For the exercises, very important, take a good look. If we divide again by 2, what I just said is still valid. That is, another half-life will pass. So, here we will be 16 days. 2 half-lives. You understand, if I divide by 2 again, I will have 3 half-lives. Compared to the initial situation, we have divided by 8. Be careful. Here, we divide each time by 2, and on the x-axis, which is the axis of the durations, we add each time a half-life. 1 half-life. 2 half-lives. 3 half-lives. 3 times 8 equals 24. We are at 24 days. That's it for this example. I'm going to take another, very famous, carbon-14. Here is carbon-14. It disappears to make way for nitrogen-14. Its half-life is much, much longer than that of iodine-131. It is 5,730 years. This is its half-life. It takes 5,730 years. It's written here, for a population to have. How do we know where we are? How do you know if the population of radioactive nuclei has halved, quartered, or not? Well, either we measure its activity, or we use the mass spectrometer, coupled with an accelerator, which separates carbon-14 from carbon-12. You know that stable carbon is 12. And total carbon, it's carbon-12. In fact, it's the same. Why is it the same? Because there is not much carbon-14. Even if it is this carbon that will allow us to date, there are very few. 10 to the power of -12 for this report. In other words, total carbon and carbon-12 are the same amount. I can quickly tell you about the existence of carbon-14. It comes from the interactions between cosmic rays and nitrogen from the upper layers of the atmosphere. This interaction gives carbon-14, which is found in CO2, carbon dioxide, and photosynthesis requires, this carbon dioxide will be assimilated by the plant environment. Not the minerals but the plants and animals that need carbon to grow. You know that the chemistry of living things is the chemistry of carbon. It's the same. There is carbon in everything and the carbon comes from there. This is how cosmic rays are at the origin of carbon-14, which is found on arrival in our body. You are radioactive, I am radioactive, because we are alive. I insist. As soon as a piece of wood changes status and becomes dead wood, its carbon-14 decreases. And it begins to decrease on the date of his death. A pharaoh, as soon as he is dead, if we embalm him, his mummy will have a carbon-14 level which will decrease over time. And that's it, the carbon-14 rate, which will allow us to date an object. As an example, I show you an exercise with graphic resolution. So the curve is given. We just saw her. It's this one. Here is the problem statement. I remind you, I just said, that in living organisms, the carbon-14 to total carbon ratio is constant. It's 10 to the power minus 12. We want to date a rock painting that was done in charcoal. Wood is an organism that has been alive, and after that, this organism sees its level of carbon-14 decrease. He is measured. It is no longer equal to 1.4 times 10 to the power negative 13, and you are asked to date this rock painting. That is to say, the charcoal. Using the graph, find the age of the sample. At t equals 0. The ratio R over R0 is equal to 1, since the decay has not started. So 1.4 times 10 to the power of negative 13, it's not very difficult. 1, it is there. 1.4 that would be there. If I graphically look for the value of the age, the dating, I come up with something like a little over 16,000. So I will say about 16,250. There is an uncertainty of plus or minus 40 years on the half-life and therefore some 113 years on my assessment. So I frame my answer between 16,137 and 16,363 years. That's it for this video. Thank you.